Hello, everyone. In today's lesson, we're going to dive into a very important application of differentiation. We'll be looking at tangents and normals to a curve at a given point. By the end of this lesson, you will be able to understand that the derivative gives the gradient of a curve at a point, and you'll be able to calculate that gradient. These are our two main goals for this first part of the lecture. First, to solidify the connection between the derivative and the gradient, and second, to practice calculating it. So what do we mean by the gradient of a curve? A curve, unlike a straight line, has a gradient that is constantly changing. The gradient at any particular point is defined as the gradient of the tangent line at that exact point. And as we've learned, the derivative of a function gives us a formula for this gradient. The derivative, f prime of x, tells us the slope of the curve at any value of x. So to calculate the gradient at a specific point, we simply need to find the derivative and then substitute the x value of that point into the derivative expression. Let's look at a clear example of this. We're asked to find the gradient of the function y equals 5x cubed at the specific point where x equals 2. Our first step is to find the general formula for the gradient, which is the derivative. Using the power rule, we bring the power of 3 down to multiply by the 5 and then reduce the power by 1. This gives us dy dx equals 15x squared. This expression tells us the gradient for any x on the curve. Now for the second step, we want the gradient at the specific point where x equals 2. So we substitute 2 for x in our derivative expression. We get 15 times 2 squared. 2 squared is 4, and 15 times 4 is 60. So the gradient of the curve y equals 5x cubed at the point x equals 2 is exactly 60. It's that straightforward. Differentiate, then substitute. Let's recap. We've now seen that the derivative is the key to finding the gradient of a curve, and we've practiced calculating this by substituting a point into the derivative. We have successfully met our initial objectives. Now that we know how to find the gradient of a curve at a point, let's use that knowledge to find the full equation of the tangent line. Our goals for this scene are to recall the point-slope form of a line and then use it to find the equation of a tangent. So we'll be combining our new calculus skill with some fundamental algebra about straight lines. First, let's remember the most useful formula for the equation of a straight line when you know its gradient and a point on it. This is the point-slope form. The equation is y minus y1 equals m times the quantity x minus x1, where m is the gradient and x1, y1 is the known point. To find the equation of a tangent line to a curve y equals f of x at a point x equals a, we need two things: the point of tangency and the gradient at that point. The point is found by taking our x value, which is a, and finding the corresponding y value by plugging a into the original function f of a. The gradient, as we just learned, is found by plugging a into the derivative function f prime of a. Let's work through an example to see this entire process in action. We need to find the tangent equation for the curve y equals x squared plus 4x to the power of negative 1 minus 5 at x equals 2. First, let's find the gradient of the tangent. This means we need to differentiate the function and then evaluate it at x equals 2. The derivative of x squared is 2x. For 4x to the negative 1, we bring down the minus 1 to get negative 4 and reduce the power to negative 2. The derivative of the constant negative 5 is 0, so our derivative is 2x minus 4x to the negative 2. Now we substitute x equals 2. This gives 2 times 2 minus 4 times 2 to the negative 2. That's 4 minus 4 over 4, which is 4 minus 1, giving us a gradient of 3. So m equals 3. Next, we need the coordinates of the point of tangency. We know the x-coordinate is 2. To find the y-coordinate, we substitute x equals 2 into the original function. So y equals 2 squared plus 4 times 2 to the negative 1 minus 5. This is 4 plus 2 minus 5, which equals 1. Our point of contact is 2, 1. Now we have everything we need, a gradient of 3 and a point 2, 1. We substitute these values into the point-slope formula. Y minus 1 equals 3 times the quantity x minus 2. This is a perfectly valid equation for the tangent line. Often, questions will ask for the answer in a specific format, like ax plus b plus c equals 0. Let's rearrange it. We distribute the 3 to get y minus 1 equals 3x minus 6. Then, moving all terms to one side gives us our final answer. 3x minus y minus 5 equals 0. So, to recap this section, We've successfully used the point-slope formula combined with our calculus skills to find the full equation of a tangent line. We found the point, found the gradient, and put it all together. All right, now that we've mastered tangents, let's move on to a closely related concept, the normal line. What is a normal line? Let's take a look. The normal to a curve at a given point is a straight line that passes through that same point but is perpendicular to the tangent line. Notice the right angle between the tangent and the normal. Our objectives here are to understand the relationship between the gradients of perpendicular lines and then use that to find the equation of a normal line. So the key new piece of information is how to handle the gradients of perpendicular lines. From algebra, we know that if two lines are perpendicular, the product of their gradients is -1. If we call the tangent gradient m subscript t and the normal gradient m subscript n, then their product is -1. This means the gradient of the normal is the negative reciprocal of the gradient of the tangent. This is the crucial relationship we need. The process for finding the normal equation is almost identical to finding the tangent equation. The only difference is in the gradient we use. We find the same point of contact, a, f of a. We find the same tangent gradient, f prime of a. But then we calculate the normal gradient by taking its negative reciprocal before using the point-slope formula. Let's continue with our previous example to make this clear. We're finding the normal to the same curve, y equals x squared plus 4x to the -1 minus 5, at the same point, x equals 2. We've already done most of the work. Let's recall what we found. From our last example, we know the point of contact is 2, 1, and the gradient of the tangent line at that point is 3. Now, for the new step, calculating the gradient of the normal. The gradient of the normal is the negative reciprocal of the tangent's gradient. So m subscript n equals -1 over 3. We now have the point 2, 1 and the normal gradient -1/3. We just plug these into the point-slope formula. This gives us y minus 1 equals -1/3 times the quantity x minus 2. Again, let's rearrange this into the form ax plus by plus c equals 0 to eliminate the fraction. I'll multiply both sides by 3 to get 3y minus 3 equals -1 times x minus 2. This simplifies to 3y minus 3 equals -x plus 2. Moving all terms to the left side gives our final answer, x plus 3y minus 5 equals 0. So we've now seen how to find the equation of a normal line. The process is just like finding a tangent, but with one extra step, finding the negative reciprocal of the gradient. We have successfully met our objectives for this section. Let's now consider a special but important case. What happens when the tangent line is horizontal? Our learning goals here are to identify when a horizontal tangent occurs and to determine the equations for both the tangent and the normal in this situation. This case is quite intuitive once you see it, and it often appears in problems. A horizontal line has a gradient of 0. Since the tangent's gradient is given by the derivative, a horizontal tangent occurs when the derivative is equal to 0. So, if we calculate the derivative at a point x0 and find that it's 0, we immediately know the tangent line is horizontal. The equation of a horizontal line is simply y equals a constant. Specifically, it will be y equals the y-coordinate of the point of contact. So the equation is just y equals y0. Now, what about the normal line in this case? The normal is perpendicular to the tangent. What line is perpendicular to a horizontal line? It must be a vertical line. A vertical line has an undefined gradient. This makes sense as our formula for the normal gradient mn equals -1 over mt would give -1 over 0, which is undefined. The equation of a vertical line is x equals a constant. It will be x equals the x-coordinate of the point of contact. So the equation is x equals x0. Let's see this with an example. Consider the function f of x equals x squared minus 4x plus 5. We want the tangent and normal at x equals 2. First, let's find the point of contact. At x equals 2, the y-coordinate is 2 squared minus 4 times 2 plus 5, which is 4 minus 8 plus 5, which equals 1. So our point of contact is 2, 1. Next, let's find the gradient of the tangent. The derivative, f prime of x, is 2x minus 4. Evaluating this at x equals 2, we get 2 times 2 minus 4, which is 0. The gradient is 0, just as we discussed. Since the gradient is 0, we have a horizontal tangent. Its equation is simply y equals the y-coordinate of our point, so the tangent line is y equals 1. The normal line must be vertical. Its equation is x equals the x-coordinate of our point, so the normal line is x equals 2. If we look at the graph of this parabola, we can see this clearly. The point 2, 1 is the vertex. The tangent line at the vertex is the horizontal line y equals 1, and the normal line, which is the axis of symmetry, is the vertical line x equals 2. To summarize, we've now covered the special case of horizontal tangents, which occur when the derivative is 0, and we know how to write the equations for both the tangent and the corresponding vertical normal. So far, we've been given a point and asked to find the tangent. Let's now flip the problem around. What if we are given a gradient and asked to find the point or points on the curve that have that gradient? Our objectives will be to find points on a curve with a specific gradient, and then apply this to find tangent lines that are parallel to another given line. This is a common and very useful type of problem. The logic is straightforward. The derivative, dy dx, is the formula for the gradient. If we are given a specific value for the gradient, we can set our derivative expression equal to that value and solve for x. So we set f prime of x equal to the known gradient, and then we solve the resulting equation for x. Let's try an example. We want to find the x values on the curve y equals x cubed plus 6x squared plus 2, where the gradient is exactly 15. First, we need the derivative. The derivative of our function is 3x squared plus 12x. This is our formula for the gradient. Now we set this expression equal to the desired gradient, which is 15. So we have the equation 3x squared plus 12x equals 15. This is a quadratic equation, so let's solve it. First, I'll move the 15 over to the left side. I can see that all the terms are divisible by 3, so I'll divide the entire equation by 3 to simplify it. This gives x squared plus 4x minus 5 equals 0. This quadratic factors nicely into x plus 5 times x minus 1 equals 0. This gives us two solutions, x equals -5 or x equals 1. So there are 2 points on this curve where the tangent has a gradient of 15. Let's look at a slightly more complex version of this idea. Here, we need to find the tangent lines to the curve f of x equals 5x cubed minus 2x plus 1 that are parallel to the line y equals 13x plus 8. The key piece of information here is parallel. Parallel lines have the same gradient. The gradient of the line y equals 13x plus 8 is 13. So, we are looking for points on the curve where the tangent gradient is 13. This means our target gradient is 13. The problem is now just like the last one. The derivative of our function is 15x squared minus 2. We set this equal to 13. Adding 2 to both sides gives 15x squared equals 15. Dividing by 15 gives x squared equals 1, so the x-coordinates are 1 and -1. The question asks for the tangent lines, so we need to find the full equations. For x equals 1, the y-coordinate is f of 1, which is 4. The point is 1, 4. The equation is y minus 4 equals 13 times x minus 1, which simplifies to y equals 13x minus 9. For x equals -1, the y-coordinate is f of -1, which is -2. The point is -1, -2. The equation is y plus 2 equals 13 times x plus 1, which simplifies to y equals 13x plus 11. So we have found the 2 tangent lines to the curve that are parallel to the given line. We've successfully learned how to work backwards from a known gradient to find the points of tangency. Now for our final and most advanced type of problem. What if we need to find a tangent to a curve that passes through a point that is not on the curve itself? This is a trickier situation, but it relies on a very important principle about tangency. Our objectives are to understand the conditions that must be true at a point of tangency, and then use these conditions to solve this more complex problem. Let's break down the core idea. At the specific point of contact, let's call it x, between a curve f of x and its tangent line y equals mx plus c, 2 things must be true simultaneously. First, the curve and the line must touch, so their y values are equal. Second, the gradient of the curve must match the gradient of the line, so f prime of x must equal m. These 2 conditions are the key to solving these problems. Let's tackle a problem that uses this idea. We want to find the tangent lines to the curve f of x equals x to the 4th minus x, which pass through the external point 0 minus 3. First, notice that the point 0 minus 3 is not on the curve because f of 0 is 0, not minus 3. Since we don't know the point of contact, let's give it a general name, say a. The point of contact has coordinates a to the fourth minus a. Now, let's write the equation of the tangent line at this general point a. The gradient at a is given by the derivative f prime of a, which is 4a cubed minus 1. Using the point-slope form, the equation of the tangent line is y minus a to the fourth minus a equals 4a cubed minus 1 times x minus a. This is the equation for any tangent to the curve. We need the specific tangent that passes through our external point, 0 minus 3. So, we substitute x equals 0 and y equals negative 3 into our tangent line equation. This gives us an equation that only contains the variable a. Now we just need to solve this equation for a. Let's simplify both sides. The left side is negative 3 minus a to the fourth plus a. On the right, distributing the negative a gives negative 4a to the fourth plus a. We can subtract a from both sides. Then, adding 4a to the fourth to both sides gives 3a to the fourth equals 3. This simplifies to a to the fourth equals 1, which means a can be 1 or mag is 1. These are the x-coordinates of our 2 points of contact. Finally, we find the equations of the two tangent lines. For a equals 1, the gradient is m equals 4 times 1 cubed minus 1, which is 3. The line has gradient 3 and passes through 0 minus 3. Its equation is y equals 3x minus 3. For a equals negative 1, the gradient is m equals 4 times negative 1 cubed minus 1, which is negative 5. The line has gradient negative 5 and passes through 0 minus 3. Its equation is y equals negative 5x minus 3. This is a challenging problem type, but by defining a general point of contact and using the fact that the tangent must pass through the external point, we can solve for the unknown and find our lines. We have successfully met our final objective. Finally, let's talk about how technology can help us with these problems, especially when we encounter functions that are difficult or impossible to differentiate by hand. Our goal here is simply to learn how to use a calculator to find the numerical derivative at a point and apply it to find tangent and normal equations. This is a practical skill, especially for exams where a graphing calculator is allowed. Most graphing calculators have a function that can numerically calculate the derivative of an expression at a specific point. You don't need to know the differentiation rule. You just need to input the function and the x value. The syntax might look something like this. You provide the function, the variable, and the point at which you want to evaluate the derivative. Let's see how this works with an example involving a function we haven't learned how to differentiate yet. We need to find the tangent equation for y equals 4 times the natural log of x at x equals 1. The first step is to find the gradient using our calculator. We would enter the function 4 ln x and the value x equals 1 into our calculator's derivative tool. The calculator will compute the gradient and return the value 4. So we know our gradient m is 4. The second step is to find the point of contact, which we can do by hand. We substitute x equals 1 into the original function. The natural log of 1 is 0, so y equals 4 times 0, which is 0. Our point of contact is 1, 0. Now we have the gradient m equals 4 and the point 1, 0. We can write the equation. Using the point-slope formula, we get y minus 0 equals 4 times x minus 1, which simplifies to y equals 4x minus 4. And that's it. The calculator did the calculus part for us. Of course, if we needed the normal line, we would do the same first step, get m equals 4, then calculate the normal gradient as 9 is 1/4, and proceed from there. So, technology is a powerful tool that allows us to tackle these problems even with complex functions. Let's do a quick summary of everything we've learned today. All right, let's wrap up and review the key concepts from today's lesson on tangents and normals. We covered a lot of ground, building from a core concept to several different types of problems. First, and most fundamentally, the derivative gives us the gradient of the tangent line to a curve at any point. The gradient of the tangent is found by evaluating the derivative at the point of interest. Second, we use this to find the equation of the tangent line using the point-slope formula. We find the point x sub 1, y sub 1, and the gradient m sub t, and substitute them into the formula y minus y sub 1 equals m sub t times x minus x sub 1. Third, we define the normal line as being perpendicular to the tangent. This means its gradient is the negative reciprocal of the tangent's gradient. We use this new gradient with the same point to find the normals equation. We then looked at several problem variations. We saw how to handle horizontal tangents where the derivative is zero. We learned how to work backwards, solving f prime of x equals m to find points with a given gradient. And we tackled the advanced case of finding tangents from an external point by setting up and solving a system of conditions. Finally, we saw how technology can simplify the process of finding the gradient. Make sure you are comfortable with all these scenarios. Practice is key to mastering these skills. That's all for today. Thank you.